moving along with our electromagnetic radiation, we have something that is called the atomic emission spectra. So when we have an electric current pass through a gaseous element, the electrons of the element or the gas are energized. They get more energy. And this energy causes them to emit light. This is how a light bulb works. We pass electric current through it and the atoms get energized and we get light. So when atoms absorb energy, their electrons move to higher energy levels. And then when they return back down to the lower energy level, they lose the energy by giving off light, emitting light. The photoelectric effect was discovered by Albert Einstein, where he actually figured out that light also has particle-like characteristics. So what he did was he put light directed towards a piece of metal, and then he was able to see that electrons were emitted from the metal. So the electrons were shot off the metal. And so by doing this, Einstein was able to show that light was made of packets of energy, quantum, called photons. So these photons were like particles. So this is a picture of his photoelectric effect. And he actually found that depending on the type of light that he shown on the metal, sometimes an electron wasn't even emitted at all. So like if you look at the red over here, there's no electron given off. And with the green there is, and with the purple or violet there is, and it's given off with even more of a velocity. And so that has to do with the energy involved with the different types of light. With his findings, Einstein later verified Max Planck's first relationship between the quantum of energy and the frequency. And so E is the energy of the photon equals H, which is the constant 6.63 times 10 to the negative 34, times V, which is the frequency. So the same as in the speed of light equation. So we can use this equation to solve for the energy of the photon. Okay, and by this, Einstein proposed that the EMR, the electromagnetic radiation, is absorbed by matter only in whole numbers of photons. So you can't have half of a photon. And in order for an electron to be ejected from a metal, to be given off from a metal, it must have a minimum amount of energy to do that. So that's why the red light didn't work. So we're going to use our energy equation to solve for energy. Okay, so what is the energy of a photon of microwave radiation with a frequency of 3.2 times 10 to the 11th hertz? So in this problem, we are trying to find energy. E is what we want. And we are given a frequency of 3.2 times 10 to the 11th. So the frequency symbol, don't forget, is V. So we're going to plug that number in for V. Well, we know H because H is the constant, 6.63 times 10 to the negative 34. So we can go ahead and solve for energy. We'll take 6.63 times 10 to the negative 34 times our frequency of 3.2 times 10 to the 11th. When you type this in your calculator, you probably should do 6.63 EE negative 34 times 3.2 EE 11 equals, and you should get, with correct significant figures here to save time, 2.1 times 10 to the negative 22nd joules. Our unit on energy is joules. Okay? So 5, 6, 7, and 8 on the wave equation practice homework assignment are using this equation. 5 and 6 are simply like this example, and 7 and 8 are multi-step problems. So let's go ahead and finish.
Don't stop believing.